Okay, Chem 1110 students, now we're going to talk about the second topic in Chapter 9, and that is acid-base reactions. So just as a reminder, acids and bases both can either be strong or they can be weak, and a strong acid or a strong base is a strong electrolyte, and they totally dissociate. And here is a list of strong acids, the same ones we saw in the last table, and we've added 8 strong bases. One of the things to remember, though, is the majority acids are weak acids, so it's pretty easy. Just memorize the strong ones and you know any other ones will be weak. So we're going to talk about the definitions of what makes an acid or what makes a base. And the first definition was by Arrhenius, and he said that an acid is something that ionizes in water and produces hydrogen ions, such as HCl, and we usually write it like this. An Arrhenius base, according to Arrhenius, is something that dissociates in water and produces OH ions. And so these are generally going to be those strong bases that were listed in our last table. Hydroxides of group 1A and the heavier members of the group 2A groups. And so you have sodium hydroxide, and it dissociates and produces a hydroxide ion. So those are strong bases. However, one of the most important common bases was ammonia, and it doesn't fit the definition of an Arrhenius base. So therefore, some years later, Brønsted came up with a sort of an improved or broader definition, which includes ammonia. And that is that a Brønsted acid is a proton donor. So obviously, if it produces H plus like HCl, then it's a proton donor. And a base is a proton acceptor, so you still can get acid-base reactions. And in these definitions, a proton refers to a hydrogen ion that's lost its electron, and we also will look at that later as a hydronium ion. But here's just a little diagram of how ammonia can be a base, because it accepts a proton from the water, creating that NH4 plus ion, that ammonium ion. All right, so when Brønsted acids donate their proton to water, it creates a hydronium ion, which is an H3O plus. And so all of these three forms of talking about that protonated water are equivalent: a hydrogen ion, a proton, or a hydronium ion. And this is a reaction of HF, which is a weak acid. You see we have the double-headed arrow there, donating a proton to water, creating a hydronium ion, and leaving the fluoride ion. So there's a couple other definitions we want to make sure we understand. A monoprotic acid only has one proton, monoprotic. Hydrochloric acid is an example of that. There are polyprotic ions. They can have more than one acidic hydrogen, and sulfuric acid is an example of that. But it's actually a diprotic, H2SO4, so it has 2 acidic hydrogens, and those hydrogens or protons are lost in a stepwise fashion, and this reaction shows that it loses the first one and creates HSO4 minus ion. That ion can then go on and lose a second hydrogen, and leaving the sulfate ion. And you can see the notes there that that first ionization is very strong. It completely dissociates, where that second step, where the HSO4 minus releases the proton, is not as complete, we have the double-headed arrow there, and because of that, that total loss of 2 hydrogens is not complete. Bases can be named in a similar fashion. If they only have one hydroxide, it's called monobasic. Sodium hydroxide is an example of that. But there are some strong bases that produce more than one hydroxide ion, and barium hydroxide is an example of that. Barium is a alkaline earth metal, and so it has 2 hydroxide ions, and therefore it's a dibasic base. Okay, so acids and bases react together and they neutralize one another, and so we're going to look at acid-base neutralization reactions. And generally, when the two react, you get water and a salt, and that's where the term neutralization comes from, is that the solution in the end is neither acidic nor basic, but it's just plain water. And so if you have HCl reacting with NaOH, you can see you get water, and the salt is sodium chloride. The net ionic reaction, if you were to write this, you'd have sodium on both sides and chloride on both sides. Those would be canceled out, and so you get just the formation of water. Okay, so the thing that goes along with this is a discussion of the pH scale, because acids and bases have been known for a long time, and people wanted to have a way to order them and say which was strongest or which would make water the most acidic or the most basic. So it is known that the acidity of a solution depends on its concentration of hydronium ions, and so the pH scale is a logarithmic scale because the effect of the concentrations cover a very wide range. So therefore the pH is the negative base 10 logarithm of the hydronium ion concentration, or pH is minus the log, and notice it's an log, so that's a base 10 log of the hydronium ion concentration. And then you can also solve that such that the hydronium ion concentration can be calculated if you know the pH by raising 10 to the minus the value of the pH. In pure water, the hydronium ion concentration is 1 times 10 to the minus 7th, and therefore if you're calculating the pH of that, you get a pH of 7, so that is neutral. Another thing to remember is that pH is dimensionless, so when you go to do problems, you don't put a dimension in any fashion after it. Here's a pH list, or a scale, if you will. pHs go from 1 to 14, and they can actually be outside of that range, but this is considered the pH range, and you can see that numbers less than 7 are acidic, numbers greater than 7 are basic. So here is an interesting table talking about some common fluids such as stomach acid, milk, tears, and how much that varies in pH. So the saliva in your mouth, which begins the digestion of food, has a pH that's much more neutral, slightly on the acidic side, but when it gets to your stomach, it's a pH of 1. So if you just think about the effect of those extremes in pH, it's very clear that the biological systems can handle pH differences quite well. So here's an example of determining the pH where you have hydronium ions of 3 different values, and we will discuss these in class. And here's another one where you want to calculate the hydronium ion concentration when you know the pH. So one of the things that's really used a lot is that reaction of acid and base producing water. And this leads to a special kind of reaction, or experiment that's known as a titration. So you can determine how much acid is in a solution by adding base to it until it's neutral, or vice versa. If you want to know how much base there is in something, you add acid to it in a controlled fashion, and that's known as a titration. It's a volumetric technique that uses burettes, which are very well calibrated. You go till that neutral point where the pH would be 7. That's called an equivalence point. And here's a little demonstration of someone doing a titration with a burette. It has a little stopcock so that you can add the base in a very controlled fashion. And you can see that it's turning pink. Well, that equivalence point is usually signaled by a color change, which is brought about by an indicator. An indicator is something that has different colors, whether it's in an acid or a base, and you have to choose the indicator so that the color change of the endpoint is very close to the equivalence point. Phenolphthalein is one of the most common, and if you did ink titrations in high school, you probably would have used phenolphthalein. So the endpoint turns sort of a fuchsia color. And here's an example problem. Want to know what volume of 0.203 molar sodium hydroxide solution would be needed to neutralize 25 mils of this sulfuric acid. And once again, we'll do that in class. All right, we're ready for the next section of Chapter 9.